Last time we talked about partial derivatives, and we looked at partial derivatives as a derivative for just the regular function from R to R. If we flatten out our curve by fixing one of the variables, we let y equal to b and we let x equal to a separately. And then for each of these, we came up with the slope of the tangent line doing some rise over run business. So this is the drawing that we had last time. And this is where we're going to go from starting today. Okay? So what I want to do is I want to create a tangent plane. So what the tangent plane will help us find geometrically is going to be a plane tangent to the curve at the point. You know, whatever curve it may be, if you zoom in close enough, it'll just look like a flat plane. Kind of like for those curves, if you have a curve, if you zoom in close enough, it's going to look like a line, and that line that it looks like is actually the tangent line at that point. Or better yet, think about the Earth being a sphere. If you look at where we are as something really small and zoomed in into your particular area, then you're thinking about you living in a flat piece of space. But realistically, if you zoom out enough, you see that you're actually on a sphere and the whole thing's not so flat. That's the Columbus thing, right? Sailing around the world, or Copernicus, or whoever. Anyways, so that's one aspect of looking at a tangent line or tangent plane. Another aspect is we can actually use a tangent plane as a linear approximation, which in most cases, that idea of a linear approximation is more of an older topic, I think, because they use that to help find approximations if you don't have these big computers to do your calculations for you. So that's kind of like an olden day activity or exercise, but I think it's also important to look at because we study these things as if they were what's called differentials, and that's another topic, a more mathy topic. All right, so we're going to create a tangent plane. And the way we're going to do this tangent plane is going to be a little bit, I don't want to say strange, but what do we need for an equation of a tangent plane? Point and a normal vector. So we need a point and a normal. So we have a point. In fact, our point is given by A, B, remember? C? That's what Mimi said. But we can actually write it as f of AB. That's essentially putting your two-dimensional point, AB, into the z function, which gives us the height, which gives us this z component. So we have a point. So now we just need a normal vector. What are some ways to find normal vectors? I don't know if that's a good question. What? A cross product of two vectors, right? So if we can find two vectors that might be on this tangent plane, if we cross them, then we can get a a normal, right? So I'm looking at what we need. We need a normal vector, and we're kind of taking steps back to see how we can create that normal vector. So we can create the normal vector by finding two vectors that are on the tangent plane, right? How are we going to find two vectors that are on the tangent plane? See if you can look at my beautiful drawing. Find 2 points. 2 other points, but the 2 points, if I find another point, it'll probably be on the plane, on the surface, so it's not going to be exactly on the plane. That's close. So on the xz plane, we've talked about partial derivatives, and so we have control over the tangent lines for two-dimensional drawings, right? So, but if this is a tangent line to this blue curve that's flat on this plane, we can imagine that tangent line to that blue curve also being tangent to the surface. If you look at a surface, imagine a sphere or something smooth, right? And if you pick a point there, how many tangent lines can you possibly have on that smooth surface? What? 1 tangent line? A lot. Infinite, yeah. So we actually have a choice of infinitely many tangent lines that we can come up with. But we'll just settle for 2. 1 going along the x and 1 going along the y. So those 2 tangent lines, which happen to be tangent to this two-dimensional picture over here, those 2 tangent lines can work to help us find our vectors. And these tangent lines will be on the tangent plane. So there's going to be an infinitely many tangent lines that we can choose. We'll choose the one that goes along the x, and we'll choose the one that goes along the y, because we know a little bit more about them. Okay? So are we good with that idea? All right. So let's think about this. I have a line. I want a vector. That's going along that line. Now, I don't really care how long the vector is, as long as I can get that vector. Right? So let's take a look at that vector. And what if we... Oh, before I ask that question, I forgot what I was going to ask now. What is the slope of this line? Remember we did this? What's the slope of this line? The derivative, okay? So this is the derivative of something, and I'll fill in a couple of things, and I'll ask you which derivative it is. This is the derivative evaluated at that point AB. So I'm going to say FAB, but I'm missing something here that's really important, and that is which derivative it is. Derivative with respect to x or with respect to y? With respect to x, I'm moving along the x. My y is fixed, right? I'm moving along my x, so this is fx. So remember, fx, or the partial of f with respect to x, either one of those would describe the derivative there. Okay? All right, so the derivative is a scalar number. After you put in the AB, it becomes a scalar. It's actually a scalar anyways before you put in the AB. But you put in the AB, you're just going to get a number out of that. So that number is a slope of that line going along the x-axis where y is fixed. I want a vector out of this. I want a vector out of this. Okay? So I'm going to call this, what should I call this? V in the x direction. Let's call it Vx. I'm going to do this in red. Vx. Now, I need to fill this with three things: an x component, a y component, and a z component. Now, one of those components should be obvious. The other two, let's talk about the other two. You probably want to do the obvious one first, but let's take a look at the other two that's not obvious. And what I'm going to do is I'm going to make a vector. Remember, it doesn't matter how long this vector is, right? So I'm going to make the vector so that the vector running along in this horizontal direction is 1. Okay? Now think. The slope of this line is a derivative with respect to x. This vector is on that line. I have my x component of that vector to be 1. The slope is the rise over the run. Now, can you tell me what this vector is? What's in the x component of this vector? One. Let's pause for a minute, because this is really exciting. Why did you say 1? It's the side of the vector. I just said this is 1 going along in this direction, right? So x is 1. All right. Thanks, Rick. Next, what is y? Y is the easy one. 0. Why is it 0? It's parallel to the xz plane, and I'm not moving along the y, so I'm fixed at 0. So, what's my last component? Rise over run, slope. Run equals 1. It's just the partial derivative. Why? Because it's the direction it's moving in. The change in z is, in fact, the partial derivative that we've been talking about. It was what we said yesterday. The slope of this line is a partial derivative. Now, the slope is equal to the rise over the run, and the slope, we said, was equal to f of fx. So you can make an equation out of this. You can say, oh, what if I didn't know what this is? That's what I want. So what if I didn't know what this was? Let's call this delta z. So I don't know what delta z is, but I know that the slope, which is equal to fx, is actually equal to the rise over the run, delta z over 1. So that means delta z must equal to fx. And when I say fx, I actually mean fx evaluated at a and b. Okay? That was pretty deep. Does that make sense? We got one vector. That's moving along the x direction. Okay? We could play the same game to get the y vector going in the y direction, or I could just tell you what it is. Vy will equal to what? Doesn't move in the x component, doesn't move in the x direction, so this is 0. And if we draw that same rise over run business, if you make the run equal to 1, the run goes along in the horizontal direction. In this case, it's the y. And the slope of this line, we said, was the partial derivative of f with respect to y. Then we have fy. That is our second vector that's tangent to the surface, that is on the tangent plane. Now we have two vectors that are on the tangent plane that we're looking for, and that's how we're going to get our normal. Okay? Is it exciting yet? Yes?
So will part derivative be a number, or what do you
It should be a number, because you'll need to put in a and b. And so when you put a and b in, then you should get a number out of it. And by number, you mean scalar, yeah. All right? All right, let's take this to the next page. Let's collect what we have so far and reiterate some of the things that we need. We need a point and a normal. We said we have the point already, a, b, and f of a, b. And the normal, we can get our normal, have two vectors, vy, vx, vx and vy. So all we need to do is we need to cross those two vectors and we come up with our normal vector. And then from there, we use the formula to find an equation of the tangent plane. Chris? That's a good question. How do we know which one to cross first, Vx or Vy? If we cross Vx, Vy, which way is my vector going to go? I want to draw a vector that's perpendicular to this. Out? So I'll say up. And if I cross Vy and Vx, it would be going down. So how do you know which vector you want? What's the right answer? It doesn't matter. Right? Yeah, it's going to give us, it should give us the same equation. Whether we take one or the other, it's going to be off by a negative sign. But, you know, when we put it all into the equation of the plane, it shouldn't matter. It better not matter, because that's how, you know, we need any normal vector. It doesn't matter how long it is, how short it is, which direction it's going. It should still give us the exact same equation of the plane. So the answer is no, it doesn't matter. All right? So let's pick one. Which way should we cross this? X and Y? Okay. So let's call it N, Vx cross Vy. So Vx was, which one was Vx? Vx, 1, 0. 0, 1, Fy. There's a certain way that I want this crossed usually, but I guess since I say it doesn't matter, then it doesn't matter. It really doesn't, but I like to see it come out a certain way. So, here's what we have. We do the cross product. Let's see. In the x, I have 0 times minus fx, so this wasn't the way I wanted, but let's deal with it. If we cross out the j component, this will be a negative. It'll be fy minus 0. And then the k component is 1. Had you crossed it the other way, you would have gotten a positive fx, positive fy, and negative 1. Okay? So there's a 1 in there. Yeah? That's just my own personal preference. I like negative 1 for some reason. Yeah, but in this case, it really wouldn't matter in this case. All right. We have a normal. We have a point. Let's make the equation of a plane. Geez, you remember how? So A is our normal vector, and this is like your A, your B, and your C. I am going to pretend that we crossed it the other way. It doesn't matter. Keep telling yourself that. All right. So what we have now is fx, and I'm going to put the full notation here with a and b that you're going to put in. So fx evaluated at a and b. So that's like your first component of your normal vector times, what was it again? X minus x naught. What's our point? Our point is A, B, and C, right? So x minus A. So Fy evaluated at AB, that's like this capital B from our normal vector, times x minus, y minus y naught, in this case it's B, plus, well, it's negative 1, right? So minus z minus f of AB x minus A. So this is your equation of the plane. If we move things around, which sometimes we might be interested in doing so, like maybe getting z by itself so that you can write it as a function of f of x and y, you can imagine z going to the other side and everything else staying on this side. So I'm going to rewrite this first one, though, the constant by itself. So that's f of AB. And then the z is taken care of, and so I just rewrite the rest of them. F sub x, AB. Remember that f of AB, f sub x of AB, and f sub y of AB are just numbers. So either one of these equations would work for us. Okay, so like I said, I said it doesn't matter, but I like this second normal better because there's -1. Because somewhere along the line, somebody's going to ask, where does the -1 come from? Well, the -1 comes from the cross product, right? So I don't ever have to hear that question anymore, right? When you're doing something and I say, oh, it's supposed to be -1, and you're going to say, where's the -1 come from? The cross product. Okay? So if you ask me that question, I'm going to take off 1 point from your final exam. Put it in my pocket. All right, let's do an example. Let's pick a surface. Should we just do one of the surfaces that we've seen before, like the saddle? Or wait, should we do a homework problem?
When people ask where the -1 comes from, you should say from their final exam.
Oh, for your final exam. Thank you very much. I'll take that. I don't mean to discourage you from asking questions, because I do want you to ask questions. But this one particular question, since we've already now spent this much time talking about it, just trying to make things unforgettable. What section are we in? 3, 4, 4, 14.4. So apparently the lab of 14.4, which was due yesterday, was set to be due at 12:45 in the afternoon, which is not what I meant to do. So I have extended it to be due tonight at 11:59. Okay? But this is just the lab, so it's not that big of a deal. Let's do the first one. This looks easy enough. So it says to find an equation of a tangent plane given to the surface at the specified point. The specified point is 777. And just to be sure that this actually works out, if this is our f of x, y, then that z component, which we've been calling f of AB, should be equal to f of 7, comma 7. 7 for x, 7 for y. And if you put 7 for x, 7 for y, you're going to get the square root of 7 times 7, which is equal to 7. So we didn't have to do that, but that's your C value from your point. Okay? Now, the next step is we have a point. We want a normal vector, and that normal vector, since we actually went through the work already, I don't need to see this work on a quiz or exam situation anymore. But I would expect you to know it anyways. So, according to the formula, we need partial derivative with respect to x and a partial derivative with respect to y. So let's say fx evaluated at xy is equal to the derivative of this thing with respect to x, assuming y is constant. It's going to be, what's this line here? It's going to be the derivative of the square root is going to be 1/2 times this thing raised to the negative 1/2 times the derivative of the inside. Again, the derivative of x with respect to y, or the derivative of this with respect to x, where y is constant. What am I going to have out here? So if I rewrite this, just so you don't have to simplify this, but I think it might be good to look at it in the simplified version so that you can anticipate what the next one might look like or be able to plug in the values. I think I have a y up on top, and then the 2 in the bottom, and then the square root of xy. I don't know if this will help you any in putting in the values 7, 7 for x and y. But in this step over here, I'm not going to put an equal sign because it's not equal to. I'll say fx evaluated at a and b, in this case 7, 7, is equal to, now I put that stuff in. So I think it's, what is it, 1/2? So 49 square root is 7. You cancel the y and then that, and then the 2 is left. So I think it's, is this right? Okay. All right. So this number, 1/2, is going to be your capital A from your normal vector, right? So Fy, and I won't go through the whole thing because I know this looks a lot alike. So I'm just going to say x over 2 square root of xy. And then when I put 7, 7 in there, I'm also going to get a 1/2. So the negative 1 then would just give me my z component. So I can memorize the formula for a quiz. You might need to memorize it and try to remember it. But in an exam, you know, you guys get a page of notes, so you can write this down if you need to. But the formula says that I have a 1/2 x minus a plus a 1/2 y minus b minus the negative 1, so minus z minus f of ac, which is the z component of the point, is equal to 0. Right? And if I didn't use this one, I use the other one instead, I think it's just as easy. Z is equal to f of xy, or fx evaluated at ab, x minus 7 plus fy. Oh, I usually put the, I said I usually like to put the number first, right? I'm going to move this over a little bit. So I want to put that number first, the z component, which is 7. One of those things that don't matter again, but yeah, probably. One of the things that does matter. Yeah. All right. So these are the two versions of the plane. Okay. So I like the first version, and we're going to, well, I'll do that later. The second version becomes important for us because of a special type of concept that's studied in Calc 1 and now in Calc 3 again, and that is called linearization. Oh, that's not what I wanted to do. What do I want to do? Copy, okay. So, oh, I don't want that one. So this is almost along the lines of epsilons and deltas in Calc 1. It's one of those things where professors usually talk a little bit about and gloss over. And they may ask you a question on an exam and stuff, but it's usually not something that you remember. Things that you remember in Calc 1 is probably, you know, derivative, product rule, quotient rule, which is the important stuff. And the not that it's not important, but the not so essential in moving on would be like related rates and optimization. Optimization is important. But related rates usually we tend to forget about them. So linearization, did I spell that right? Linearization. Linearization is one of those things where you're using a line to estimate your graph. So the idea behind linearization is essentially this whole thing about zooming in, so that if you have a graph, as curved as it may seem, if you zoom in enough, this curve over here, which is curving, which is a little bit more curved, now zoomed in, looks like a straight line. So that's the same idea with linearization with surfaces. You zoom in enough, it looks like a plane. In fact, in the graphing programs that we've seen, they actually use these things. They actually use planes to make those surfaces. They just connect a whole bunch of planes together. Just like here, they have a lot of points. They connect those points with a line, and if you zoom out enough, it looks like a curve. So that's the same idea. That's the deal with linearization. And so with linearization, they write things almost like this tangent line idea, but they change a couple of symbols for certain things. So this is what I wanted to copy, because this is the generic form of our equation of the plane. And I want to start off with this equation and talk about how they address linearization. So the idea behind linearization is that they start off at a specific height. This is your height. This is your z value, your z naught or your c. So you start off at a particular height. So that height is going to be the f of AB, right? And now the linearization happens when you move along the x and you move along the y and have those contribute to your offsets, your placements. So what they like to do is they use x minus x naught to be the offset change in the x direction. And so sometimes they end up calling this delta x. So there's an offset in the x direction, and then there's another offset in the y direction. So then the linearization becomes z is equal to z naught plus f sub x x naught y naught. Sorry, I'm changing from AB to x naught y naught. Delta x plus fy x naught y naught delta y. So this is your linearization, and there's some further information here that happens. The z naught brings you to that place where you need to be, and then the derivatives here with a change in x and a change in y kind of give you the plane that you're working with, right? So without this change here, people break this down even further and take a look at just this part, the change. That is what the differential becomes. And the differential is a change in z. So without this initial placement of where you're going, the z naught, and just focusing on how the z changes, that's what they consider the change in z. So I'll write two different equations here, but then the last one is going to be the one that they're going to use. But if we're just concerned about the change in z, then you're just really concerned about this second part, which is fx, x naught y naught, delta x, plus fy, x naught y naught, delta y. And so since we've eliminated all the offsets and we're just looking at the change, and the change is all linear, then we are now going to be allowed to call this a dz. And so this is where it becomes a differential. dz fx xy dx plus fy of xy dy. Okay. Now I also took out the x naught y naught because we can be as generic as we want to be. This can happen at any point, so we're just putting x, y generically without specifying a particular point. Okay? Let me backtrack over here again and put a box around this and call this a linearization. And sometimes, instead of calling this z is equal to something, they call it L of xy. L standing for linearization. It's using a tangent plane. Now you might think a tangent plane is not a line, but when you're talking about the general context of things, a tangent plane is a linear thing. So when they talk about linear, they mean not necessarily a line, because we're talking about a line in 2 dimensions, but when it's 3 dimensions, it's a plane. When you go to higher dimensions, you think about it as another 4-dimensional plane or a 5-dimensional plane. Okay, so the idea behind linearization just means that your variables, x and y in this case, are involved here, and they're not being raised to a power, or they're not being taken in as a trig or an ln or an exponential function of something. Okay? All right, so if we take a look at another homework problem, which I took a peek at and saw that this next one is asking for the linearization, number 2. They want you to find the partial derivatives, evaluate at some points, and then find the linearization, so they write it as L of xy. But that's really just that thing that we had, right? That formula. So let's take a quick shot at this. Then maybe we'll have time to do one more. So your function is 4. F of xy is equal to 4 plus x times ln of xy minus 7. And then your AB, or your x naught, y naught, is at the point 4, comma 2. So they want a couple of things. What they didn't have here, one of the first things that we need is the z component of this point. And I'm noticing that they didn't ask for it, so let's do it right here. So f, this is f without an x or in a y subscript, so that means I'm using the original function. F of 4, 2 is this function when I put 4 and 2 in, right? 4 plus x is 4, ln of x is 4, y is 2, minus 7. So 4 times 2 is 8. 8 minus 1 is 7. ln of 1 is 0. 4 times 0 is 0. 4 plus 0 is 4. So it looks like your point is 4, comma 2, comma the y that we just found, 4. Okay. Now we need derivatives. Let's take some derivatives here. The derivative with respect to x. So I'm going to say f sub x of xy. 0, the derivative of 4 is 0, but then now I have a product, so let's be careful and use the product rule. Derivative of the first times the second plus the first times the derivative of the second. Derivative of ln is 1 over something, and then times I need to take the derivative of that something with respect to x. What's the derivative of xy with respect to x? Y. So this is ln of xy minus 7 plus, looks like it's just xy in the numerator, xy minus 7 in the denominator. Okay. Let's find the partial derivative of f with respect to y. So 4 is still, the derivative of 4 is still going to be 0. X is a constant now, so I can leave x out there, and now just take the derivative of ln of xy minus 7. We already did that. Except when we did it, we took the derivative with respect to x. Now we need to take the derivative with respect to y. So it's 1 over that thing times the derivative of that thing with respect to y, which is x. So that's going to give us an x squared in the numerator. Okay? Now we want a linearization. If we want a linearization, we need to plug in the values of 4, 2, the a, b, or x naught, y naught into these functions. So f sub x of 4, 2. Again, the ln of this thing, since we're putting in 4, 2 all the time, it's going to give us 8 minus 7, which is 1. ln of 1 is 0. So this is 0. And then now I have 4, 2. 4 times 2 is, what's 4 times 2? 8? I thought it was 16 for some reason. 8 over 1. Right? So negative 8 for that one. F sub y of 4, 2 is going to give us 4 squared. Now it's a 16 over 1. Okay? Did I do something wrong? Questions and confused looks. I don't know. Is that better? All right, good. I think I put a plus there. Sometimes when I write, it doesn't come up on the screen. Yeah, really. Okay, I think we're done. So your linearization L is equal to the z component first, and then now the fx, which is 8, x minus 4, x naught is equal to 4, plus fy, which is 16, and then y minus y naught. And the idea behind this is that if you were to put values that are near 4, 2, if you were to put that into this original equation and you didn't have a calculator, that would be hard to compute. So this is really important for those old days where we didn't have calculators. We had slide rules and stuff like that. What? How old do you think I am, man? No, I didn't learn it that way. So without these calculators to compute these things, if I, for some reason, wanted to know what f of 4.1 and 2.3 is, and it's hard for me to put, 4.1 and 2.3 here and get a value, I would find the linearization, and if I put 4.1 and 2.3 here for x and y, that would be easier to compute, right? So that would be easy to compute, and I can get a good approximation provided I'm pretty close to this point. So that's what the linearization was used for. But now we have Wolfram alpha, so we don't have to think anymore. That's funny. So this particular problem doesn't ask for the differential, but if you're asked for the differential at any point, usually, so separate question. Differential at any point. So remember, the differential at any point is really just the second half, not even half, but the second two-thirds of that without this first number. And then if you wanted the differential at that particular point, you would use the same number, 8 and 16. But if you want to be generic at any point, then you would actually use the f of xy, or fx of xy. So you would say dz is equal to the fx, which is this whole big thing, ln of xy minus 7 plus xy over xy minus 7 times dx. Because you're saying you want this at a generic point, you're not saying at a particular xy point, a particular ab. And then you would say x squared over xy minus 7. I was just looking at this, times dy, and then you would be done. This is your differential. Okay, so the differential in general doesn't take in those values, but the linearization, you need to make sure you plug in the x, the ab, x naught, y naught, into the partial derivatives so that you get a number. And remember that your linearization is essentially an equation of a tangent plane. It's a plane, and what's important for those planes are that The x and the y values are not being squared, divided, or anything. They're just plain by itself. All right? Was that fun? Is that good for you too? Whew. Need a cigarette now.